Welcome again to the NPTEL course on storage systems. In the previous class, we were looking at some aspects relating to consistency. First, I looked at the atomic commitment problem, then we looked at the consensus problem, and then as an example of consensus problem, we looked at Paxos. So today I want to go a bit in detail with respect to another type of consensus problem, the problem of how to ensure that messages are received across multiple nodes in a what you might call a consistent manner. That is, if a node 1 sends a message to two nodes A, B, C, and then it sends a message to the same nodes A, B, C, it is required in some cases that all the nodes A, B, C should receive the first message before the second message. And if it is, you cannot guarantee this, there are some interesting problems that develop. So, we will look at this particular problem. This again is some kind of a consensus problem, but with respect to message ordering. And these are important in storage systems, because storage systems often update the state based on the messages they get, especially distributed file systems and distributed databases or distributed volume managers. Okay, so basically I need some kind of a way in which I can control the order of messaging. And for example, if you look at distributed storage systems, I have consistency fine through transactions, but transactions need ordering of writes. So how this writes are ordered is critical. But what is interesting is that most storage systems, whether it's file systems or databases or volume managers, have different needs. For example, for serializability, file system databases need control and ordering of writes, but if you order it too much, it's an overkill, because as we noticed earlier, disk systems are very slow, storage systems are quite slow, and you want to exploit abilities of multiple things going on at the same time if possible. And so, if you can relax the ordering, it is better. If you force them to go in a particular order all the time, it is too restrictive, and many interesting optimization, media specific optimizations, like for example, in the case of a disk, right, the elevator algorithm, those kind of things become infeasible. So, you do not want too much ordering, but there are sometimes you do require order. Okay. So, basically you need to have some good mixture of these two things. Okay. So, again a file system may need stricter guarantees for consistency of metadata, but may not be for data. Suppose you consider a parallel file system. In a parallel file system, it may be that a single file is being updated by multiple nodes at the same time, each node having a partial view of the file. Okay. And how these updates go to the file may not be, the exact order may not be that critical in many situations. It will be critical in some situations, but not in other situations. So, what we need is some way of controlling this order, okay, how these messages go. Okay. The other reasons also why this is important, if you are doing concurrency control, it turns out in a file system, usually you do not have that many aborts, because they are whatever transactions we do in file systems typically are sort of short duration. And so, it turns out that there are many complexities, but just for simplicity, let me just say that file systems can work quite well with redo only transactions. Because databases have often long lived transactions, you need redo undo style transactions. So, basically your messaging models and concurrency models, they have to have certain flexibility, and one size fit all does not work here. So, you need to have certain, let us say, flexibility here. Okay. But this makes it even more difficult in the presence of failures. Okay. Basically, if you have failures, what happens is that one node might be aware that a particular node has failed, some other node has failed, but the other nodes also do not have the same model, then there can be some interesting problematic situations developing. Okay. So, many times we can distinguish between control messages and data messages. So, it may be that you need total ordering for control messages, whereas you might need some ordering for data messages. For example, if you are doing transactions, you might need it, but for some other situations like parallel file systems, may not need it. One standard way of ordering messages is through timestamps, but the problem with timestamps is that you require a synchronized clock. Now, it turns out this synchronized clock is not going to be easy to do, because the accuracy is typically not very good. Typically, you get only about millisecond accuracy or worse. You don't get anything better. It could be even tens of milliseconds. And if you are talking about high speed storage systems, this millisecond accuracy is certainly not useful. Okay. So, you need other models if accuracy and resolution of these clocks are not high, you need something else. Okay. So, our basic problem is that distributed systems communicate through messages, and sometimes ordering of the messages is critical, and especially is critical for storage systems or other kinds of systems which are trying to be resilient to failures, and the way they handle failures is by having replicas. And so, if some update is done, you have to send it to the updates to multiple sites at the same time, and you have to ensure that one set updates, that is logically after some other set updates, they should also happen on these receiving sites in the same order. If they get in some different order, the logic can get completely mixed up. Okay, so that's very critical. Okay, that's what we are trying to understand. It's also useful in some other contexts. As I mentioned earlier in the previous class, real-time systems have another desperate need. They might need to have message synchronization, which is correct in spite of process or communication and failures, including Byzantine failures. Okay. You might need something like atomic broadcast of sensor readings to all nodes. For example, consider a aeroplane where there are multiple sensor readings, and you have to ensure that all those, you are doing some computation on all those readings, and they have to be essentially of the same approximate time instant. It can be two different time instants. Okay. So, you need some kind of atomic broadcast. Okay. And it is also useful in other situations. For example, we already considered one in internet. For example, if you are having mail systems, if you get a reply later than the original message, it is a problem. It actually happens in Usenet. If you are talking about some news groups, it does happen, basically because the reply comes earlier than the initial query or whatever. Okay, it happens. Okay. Same thing with cricket scores also. Okay, these things also happen. So, in many situations it is very critical, but in some of the situations it is just odd or not very pleasant, one of these things. Okay. So, I also need to figure out how to do message synchronization. Storage systems depend on message synchronization for consistency of data. If that is not guaranteed, anything can happen. Okay. So, basically what we are looking for is, I want the same information, okay, to be delivered into multiple locations in the order that the application decide, very critical. And this is what is often called group communication systems, or there is a particular specific model called virtual synchrony model. Okay. We will look into some of these things. I hope I motivated why you need this message ordering as a critical component of distributed systems. And basically it is in some sense an equivalent of a consensus problem, because here we all have to agree that everybody has agreed that they have received a particular message followed by some other message. So, all this can be seen to be some instance of consensus problems. Essentially these things are in principle difficult or impossible in theory, but we can always try to do something in spite of the difficulty in theory. Okay. Again, let me motivate one more example. Suppose you want to have shared disk file systems. Okay. So, basically what does it mean? It means that you have multiple disks which are shared by multiple operating systems, okay, and or it could even be the same operating system. So let's take care of the simple case, that is multiple disks are there and then there is a single file system which is running on all these multiple disks and it is in a storage area network. So essentially what we need to do is the storage area network gives you a block storage and I need to put a file system on it, okay. So basically all the hosts access data on disk directly via the SAN. The file system metadata is shared and concurrently updated from multiple hosts. So this is basically the reason why you want to do this for scalability and throughput. And it is the responsibility of the file system to ensure proper synchronization for both data access as well as ensure coherency of caches in the nodes. Okay. Because typically in these systems you have caching, and if there is caching, you may have to ensure that whoever has got a dirty copy of the cache, right, dirty copy of the data, it might have to be revoked and messages will be sent saying that whoever has got the dirty thing, please flush it to disk, or somebody wants to write to something and some other parties have cached it in the read mode and they all have to flush it, and somebody sends a message saying whoever has got a read-only copy, please just throw it out, so that somebody else can be given the chance to write to it, okay. So you need to do a lot of messaging so that there is some proper synchronization for both data access as well as for coherency of caches, okay. Now if this is the case, typically the reason why you want to go for this kind of models is that you don't want a single point of failure or bottleneck, okay. And that's why you need what is called a distributed lock manager. Okay. So if you're planning to do shared disk file systems, you need a distributed lock manager. We also notice NFS has a DLM also, that's usually at the application level, okay. But it turns out the DLM is a very complex entity and it is non-trivial for various reasons, for theoretical reasons as well as for practical reasons. First of all, we should mention that if there is a DLM, the DLM now is the only entity that stands in the way of availability. The DLM is, everything is now being, let us say, now everything seems to now depends on the fault tolerance of the DLM, okay. So failure of any node in cluster should not cause lock state to become inconsistent or lost, okay? This is critical. But what is our problem? Why is this so difficult? It's possible that there are other lots of interesting concurrent events that can happen. There are local events, there are remote lock requests, failures, new guys can join, etc. Okay, that is, people can exit and enter the system. Okay. Now let's think back about why there are some complexities in some of these cases. First of all, this distributed system will get to know about the system through messaging only. Okay, that's the only way it can figure out anything. Okay, so either we can use TCP kind of protocols or the unreliable datagram protocols like UDP. Suppose we use TCP. Now TCP is an excellent protocol. It provides a stream model, and what it gives you is a way in which if there are any losses, it is retransmitted so that the recipient gets the bytes in a sequence as was intended. That's why it's called a reliable transmission protocol. Okay? It's reliable only in the sense that the recipient gets the bits in the same order it was sent by the sender. So the kind of failures it handles are transmission losses, not node failures. That's important to remember. Okay? It is reliable with respect to losses during transmission. That is, intermediate networks, they drop, or the routers, they drop the packets. For that, they have a method of retransmission to handle it. But this particular protocol has not been designed with failures of nodes in the first place properly. What do you mean by that? Suppose I am sending some piece of data and then my node dies. Okay. Now there is something called keep alive in the TCP protocol, and then these are sent when there is nothing else being sent on the node, so that to keep the connection alive. It's called keep alive, and the keep alive timeout is about in terms of minutes. That is, if I die, there is no keep alive for some time. The other node thinks that everything is fine, even if I am dead and gone. So basically, a TCP that is broken, the stream that is broken, is noticed by the other peer based on most recent activity. When it has sent some messages and when did the most recent keep alive come. So because of this, if I am talking to 5 different parties, depending on when I talk to those 5 guys, each guy will have a different notion of when I died. Okay, it's not a consistent notion. Because for example, I talk to party A first, and then I immediately die. Then A thinks that I am alive for a longer period than somebody who talked much earlier, because for him, he has the keep alive etc. will come much later. Okay, sorry, will come much earlier. Sorry. So there is some kind of a lack of consensus amongst set of peers with respect to similar, whether it's alive or dead. Okay. So now, if I have different notions of alive and let us say non-aliveness, there can be some consistency problems. I will come to that in a minute. Okay, why that's the case. So stream protocols are not a solution. It also turns out unreliable diagrams are also no solution. Okay, first of all, they don't give you any ordering of any kind. At least TCP/IP give you a reliable stream. Okay, it is not able to handle failures. Okay, but it gave you a reliable set of bits. Okay, the same order in which was sent by the sender. Here, it's basically there is no ordering among messages because it's not a stream protocol. It's basically message oriented. So, but there is no ordering amongst messages, and worse, doesn't have any flow control, etc. Okay, and because it doesn't have any of these quote reasonable features, the application is going to have a lot of trouble to work around all this. It's non trivial. Okay. So basically, I need some higher level support, and one of the things that we can do is we might need a distributed consensus algorithm for agreement and membership and various other kinds of things. Okay. So again, I will explain this further. Let us go to one example. I mentioned that with TCP/IP, you might have different notions of when a node is live or dead. So I will illustrate this with a slightly different example. It turns out there are some 2 classic problems called the split brain problem and the Mexican shootout problem. What is split brain problem? Suppose I have a system with 2 nodes A and B, and they are connected through multiple different connections. This is quite a natural thing, because I might be connected, A and B might be connected through the system network, let us say gigabit Ethernet, whatever it is. Okay, I might have gigabit Ethernet running between A and B, therefore I am connected to that, typically the system network. I might also be connected through SAN, okay, to a shared storage system. Okay, that is A and B are writing through SAN to the shared disk system. That's why A and B can put some stuff through SAN and B can read from that SAN. Okay, they are connected in some way. They are not connected directly, but they are connected through SAN. Whereas this N1 is a direct connection. A sends message to B directly and B sends it to directly. Okay, it's going through the regular network. Suppose a live node A is considered dead through N1 by B, but N2 connection to SAN with A is still good. That is, B is finding that A is unresponsive. Again, there are a lot of subtleties here also, because it may be that A is temporarily heavily loaded, it is just not able to respond. So, by the FLP result, okay, basically we are talking about the fact that in a distributed asynchronous system, you can't agree on, there is no consensus possible even with one faulty node, basically because you can't distinguish between an arbitrarily slow node and a dead node, okay, there is no way to do it, okay. So, if B for some reason or other thinks that A is dead, okay, but it turns out A is still able to talk to SAN, okay. So, B is in a dilemma now, okay, it does not know what really situation, it can't figure out A's connection with SAN. Of course, there are some protocols for this also, there is something called custody reservation, you can do all those things, but let us say we are not doing it right now, because even if you have this custody reservation, I will find some other failure mode in which I can show this example, okay. That is always a way to do. I can always construct the pathological case, okay. Assuming that there is no custody reservation, those kind of things, B cannot find out whether A is actually able to talk to SAN, okay. Now, it can't keep on waiting. For example, I am interested in a highly available system. If it is unsure, it can't keep on waiting. If it keeps on waiting, that means that it has to update something, it has to keep waiting till it gets a sign of life from A through network N1. That means my system is sort of not available. So, if I do not want to get into that unavailability situation, but I still can't figure out whether A is able to talk to SAN, the only thing that I can do is, I can be optimistic and say that yes, I am not able to talk to A, most probably he is dead. If I do that, I am getting to this problematic thing, because why is that the case? It may be that A has taken some locks on the SAN to prevent inconsistent update, but since I can't figure out whether A is live or dead, I can't wait for him to drop the lock. So, since I cannot wait for him to drop the lock, I cannot take a lock, Therefore, what I should do? I should just go ahead and update it without thinking that A is alive. But that can mean that A could also be talking through SAN to the same place. That means that there could be inconsistent SAN updates, okay. So, whatever B does is going to be a problem. It does not either is unavailable or inconsistency results, okay. Now, what is one solution out of this problem? There is one solution colorfully called as Mexican shootout. What is this? If B is in a dilemma, one way to do is to be the bad person, says, I can't figure out whether A is live or dead, I will actually indeed make A dead, I will shoot him out, okay, because I have to update something, I can't figure out if A is live or dead. One way to do is to have some other mechanism by which I take the power out of the system. I guess there is some way to yank the power cable from A, and these things are available. If you talk to any highly available system design, there are various things called watchdog timers, there are various ways in which you can remove power for some other node, okay. So, B can decide to be the person to actually kill A, to make completely sure that he can go and access the SAN without any competing accesses that can make the access inconsistent. So, B can proceed to kill A because it is not able to talk to A through N1, okay. But our problem is that if the inability to talk to A through N1 by B, it could be that it is a symmetric fault. That means that if B is not able to talk to A also may not be able to talk to B, and A also can decide the same thing, exactly the same thing, okay. And therefore, he can also decide to yank the power cable from B. So, now both the systems are down and it is not available. Now, this is if you are designing for highly available storage systems, this is a problem, okay. So, you can see that underlying all this stuff is results like FLP, etc. Okay. These are the things that are actually underlying the systems, okay. So, again, basically what is the problem? If there is a fault, you do not have a consistent view of where the faults are, okay. It can be because of multiple reasons. It could be because of network problems, and that often create a lot of confusion. Okay. Actually, there is even more a serious problem. If you remember, I talked in the previous class about a result where we said that in a camel model, CAML model, when there are crashes, asynchronous, messages can be lost, and it is what does M stand for? CAML, lossy. I'm sorry, I've forgotten what M stands for. In that particular class, you mentioned that if you're not careful, in this particular model, it is possible that you can get arbitrary messages on your network, which is not connected with any previously functioning systems. Okay. I will explain this later in the next class. Okay. Furthermore, okay. So it turns out that essentially any storage system has to worry about getting all kinds of problematic messages that could be sitting there. There has to be somehow made sense of, and whatever doesn't make sense, it has to be dropped on the floor. Okay. So now let's look at in a slightly simpler setting. Okay. So again, I'm talking about ordering between messages in the context of reconfigurations. What exactly is a reconfiguration? There is a systems ABC, and then A dies, and then system gets reconfigured so that B and C only work. Okay, that's a reconfiguration. Okay, and then later A can come up and it can participate in the system. Okay. Now suppose I don't have any guarantees about ordering of data messages and reconfigurations. Okay, so in a concurrent system, this can lead to loss of integrity. What is the situation? Similar to the previous situation, right? In the split brain, you can have the same situation here. For example, let's say that A has taken a lock and it has sent a message to B. But before this message made its way to B, A died, and then after the death of A, reconfiguration took place, and the message was waiting here and there wherever, finally made its way to B. Let's say the logic is written in such a way that whenever the message of this kind comes here, it's assumed that A has taken a lock. Therefore, it is safe for B to act on it. Okay? Because people know what A is doing, you know the code of that particular system. Therefore, by definition, A couldn't have sent it without taking a lock. So B makes the assumption in the context of reconfiguration, it could be fatal, because it might be the case that A's locks might have been forcibly released in a reconfiguration, and the message comes in, and B, if it doesn't have a clear idea about the state of the system, if it acts upon this message, it can update it without a lock that A would have normally taken. Okay. So it's possible that this particular update without a protecting block, okay, can be causing system consistency to go away. Okay. Here also we can think about another situation where A dies, it can even come back up again. Okay, and even that could also happen. Okay, and so the various situations that you have to handle, if somebody writing the B's code, if they want to handle this kind of situation, reconfigurations, then they might have to think about all these cases, and if you really want to be correct in spite of all these problems, the code of B can become quite complicated. Okay. And sometimes what also happens is that if some messages have been sent to A, and these messages can be diverted to B because A died. Now, without any additional high level support for this kind of situations, then B might have to think the following: these messages are actually for A, but I'm handling them. These messages are actually for me, and I'm handling myself. Okay? So it has to keep on in its code, it has to think about all these things. So it might say, for example, this message came to A did partly some part of the processing, it sent some message, and now I have to handle all those things. I have to remember exactly what state A had done it and died. Okay, those kind of complexities B might have to think about. So this kind of code is completely impractical. It can be written, but it will be totally impossible to reason about and to get it right. It's almost impossible. Okay. It is done, people have done it, but it is extremely difficult. There is also another possibility. In the previous one we talked about the sender failing. Here we can talk about, so in the receiver can fail. Okay. So instead of sender failing, receiver could fail and recover and receive message a new incarnation. That is, A sent something, this B died, it rebooted again, the message A sent came to B, and A might be saying do something about X. Okay. Now this X could be quite different in the new incarnation, definitely possible. Okay. So it has to again keep track of history of what happened. In some sense, you need to know everything that happened before. Okay. So if you don't have this information, it's possible for you to do some wrong thing. There is also issues that crop up if you don't have message ordering, like the following example. In some old file system with a lock manager built without this message ordering guarantees, you can come across these kind of problems. Okay. What is the situation here? A is one node, there is a lock service, there is nodes A and B, there is a lock service. Now A requests a lock, but the grant of this lock takes a long time. Sometime later B requests it, and the lock service what it does is, it gives a list of the way this particular file system was constructed. It basically says, I will tell you who are all owning it. You go and talk to them and get a lock from them. That is what this owner says. Basically what has happened is that B has sent a request and it gives you the set of one, because basically it has granted it here at this point, therefore it knows who all have got it. So this guy now gives saying that I had given it to some party A and probably in some other situation some other parties, I am going to give that list here. Now B gets a list of all the guys who have got the lock. So B now will write to A saying, please revoke that, I want to get hold of that data object, please drop the lock you have. Okay. But suppose by some aspect of the network, this revoke message goes earlier than this one. Okay. Now the logic of A, the program that has been written, should be geared to handle this kind of situations. Okay. So basically what we are talking about is, it's possible that I can just drop this particular message. It may be okay in this particular situation, but there could be other situations where you can't just like that drop the thing just because saying that logically doesn't make sense. It may be that it's really required because A could have been substituting for C, D and whatever reasons. Okay, we cannot be completely sure of it. Okay. So it turns out that this revoke message is unexpected. Easiest thing oftentimes is to drop it on the floor, but without any guarantee that dropping on the floor is, let us say, safe. You'll have to, your logic has to look at the whole thing before deciding what to do. Okay. It's not a, again the logic becomes extremely complicated. Okay. So here you notice that there is something what is called a causal relationship. Okay. Suppose I use what is called causal message ordering. Okay. Basically only after grant can you get a revoke. It can't be before. Okay. So if you are able to use causal message ordering, then you can probably reason about it and then decide what is the right thing to do. Okay. Or you figure out some way in which there is what is called causal message ordering. Okay. You ensure somehow that the revoke actually comes after this grant. Okay. If you are able to do that, then the logic can be simpler. That is, somebody else is taking care of this message ordering. So what is required? one thing to notice is that concurrent systems are very difficult to reason about. Now, if you add failures to it, it becomes that much more complicated. Okay. And there have been many, just like the previous file system and the other file systems also people have designed without FIFO ordering, and this get into deadlocks. Okay. So basically it turns out if you really want to have reasonable code, at least you should have basic FIFO message ordering. Other thing that we need is timely agreement among processes about membership and system. Now these two things are connected. One is message ordering, other one is who all exist, because when I am sending messages to replicas, I need to know who is there, and everything is done through messages. That means that these two problems, there is some tight connection. I need to figure out how to do it. So I need ordering among messages with varying levels of strictness. I might have things called FIFO, first in, first out, or Causal. I will come to that soon. Basically, just an example of a Causal message ordering. Basically, you can say that these things are, once you have granted it, then only can you revoke it. Therefore, this has to be somehow made to come like this. Okay. There is some relationship between the messages. So it is causal relationship. Okay. There is also a total ordering. Basically, you wait for all the messages to go on the other side, all the replicas, completely make sure there is some kind of distributed consensus that is done across all the nodes that are getting the replica messages. And once it is completely done, then you send the next message. Okay. It's an example of total ordering. Okay. So essentially we need a strong messaging and membership system, which is often called the group communication system. And if you have this kind of system, then a distributed lock manager can use it. It makes that life of DLM slightly simpler. Because finally, as we looked at it, right, DLM is going to be your only thing that stands in between chaos and order. Okay. Everything is now for your, whether how messages are, how the data is getting flashed, or how the things are getting updated, all those things now depend on the DLM. Okay. So you have to ensure that this particular thing is rock solid. Okay. And for this to work, we need to have some way of ensuring that when you have replicas and you are sending or broadcasting messages, reliable broadcast, I need to have some kind of ordering. Okay. So one of the models that people have come up with is the following. What is needed is that all messages sent in a view should be delivered in that view itself. What I mean by a view is that a view is a particular state of the system with respect to who is live, who is dead. That is, this is with respect to failures. Okay. Every time there is a failure, there is a new view. Okay. So the system basically you can think of it as a set of views, each view being a coherent set of nodes working together. When a failure occurs, then you get a new view. Okay. So what is needed is that all messages sent in a view. For example, I am in a particular view, there are a bunch of nodes talking to each other. If I send a message in that one, preferably it should be received in the same view. It becomes complicated in case I send it in one view and it received in a different view. That means that one message has gone from one view to the other view, and the recipient has to figure out what to do with that particular thing, given that some failure has taken place. It has to do some failure processing before it can decide what to do. Okay. So basically, the program becomes that much simpler to write in case message delivery is atomic with respect to failures. This is often called the virtual synchrony model. Again, we will go through some of this in some detail. So again, I just wanted to clarify what we need is basically the application should not worry about failures if possible. If it gets a message, it should assume that it has come in the same view. Okay. Therefore, it has a consistent notion of who is there, who is not there. And all the parties who are in that particular view all have the same view. So, there is no question of any confusion. If in case a message is sent in one view and is going to be given in the other view, then there are multiple possibilities. One thing I can do is I can prevent that message to be given to the new view. I can just drop it on the floor. That is one possibility. Or I can do the other aspect. Suppose I cannot drop the message on the floor. It is an important message. I will essentially stop the whole system in some way, prevent anybody else from knowing about the new state of the system. I give the message and then only tell everybody that some particular thing has failed. I can do either of these two things. Okay. That is basically what I do is, the message is received by the node, fine, but the application does not have to know. The application is told only, the application is given the message, then only it is told that some failure is taking place. Okay. So, when a failure happens, all the messages sent in current membership must be flushed out of the system before new membership be installed. Okay. This is the dropping all the messages, okay, before a new. Okay. So, this is one thing we can do also. Okay. So, there are multiple ways to handle it. Virtual synchrony is one model, which basically tries to ensure that message sent in a view is delivered in that view itself. Okay, that's what it's called virtually synchronous. It happens in the same view. So, the GCS, the group communication system, it integrates messaging and membership. How is the membership detected? By what is called heartbeats. What is heartbeat? Every node sends a heartbeat message to every other node, and they get information saying that, and that other party also sends back a reply. Okay. That's how we know the other party is alive. Okay. Because there is no other way to know it. Okay. Because everything communicates through messages. Okay. It can be through electrons or photons, but everything has to go through messages. Okay. And we have detected only by some messages which are called heartbeats. Each message is associated with a view in which it is sent. The message is delivered in that view only. Okay. View delivery will be delayed if need be. Okay. That means that if a new view has to be notified to all the nodes, it will be delayed till the message is delivered in the previous view. Okay. So that the application doesn't have to think about that it is seeing some unusual new situation has developed. It is thinking as if it was the old situation. So, other issues like flow control etc. also handled by GCS. Okay. So, the membership list is ordered and delivered to the applications in the same order for all the members. So, that means that every member has the same idea about who is alive and who is dead. Okay. That is why we will not have this kind of split brain kind of problems. Okay. That means that some of this magic is doing something unusual. It is doing some kind of a consensus which you said is theoretically impossible, but it is doing something reasonable. Okay. So, messages can be ordered in some multiple ways, FIFO, causal or total. So, the most important thing to remember is that node gets messages in real time order, but applications in order required are specified. So, you can see the distinction. Distinction is that messages are being sent as usual, the node gets it, but the application is not told of it. So, it is buffered in the kernel, okay. Something like that, buffered somewhere, typically within a kernel. Okay. And then the applications are notified after the new view has been installed or before the new view is installed, depending on what you want. So, in this particular model, when application joins a group, it is sent a new view message. Okay. When as soon as anybody joins a group, it is sent a new view. It says who are all the parties who are there. And then the GCS after from that time onwards, controls application with data and view messages. It keeps saying everything is fine so far, keep on exchanging whatever data you want to exchange. Then suddenly one failure occurs, it is noticed some particular way, we are not going to detail how it is done. It is noticed, and then GCS will essentially flush all the messages that are still extant. Then it will send a new view message to everybody. Then all the nodes will update their node idea about what is the current state of the system. Again, they will proceed further. Okay. So on a failure or join detection, a group unstable message sent to let the application know group is not stable. So why is it done? So that application to stop sending further messages. Okay. And only when it is done, you tell the GCS. Okay. Basically, some things are critical. I want to do it actually in the same view, because application also has some notion of what is safe to do. It has been told that something has happened, but it does not want to react to it immediately because it has some even more urgent things to do. If it has figured out all the absolutely critical thing has to be done, then it goes and tells GCS, okay, now I am ready to change my view of what the situation is. Okay. So then GCS flushes all messages floating around. I think there are a lot of details we have to go through it, but I think for the time being we'll just say that after all messages are flushed, the new view is delivered. Notice that there has to be some understanding between GCS and application. If the application keeps on sending messages, then new view may never get delivered. Okay, basically because it is a cooperative model where if there is a failure, all of them have to cooperate to install a new view. If a particular node doesn't, let's say, cooperate, right, and keep sending messages, then GCS has to keep waiting because it might think that all these messages are critical. It has to be somehow sent in that particular view itself, because it has to be processed in that view itself. Okay. Otherwise, there is going to be inconsistency. So it just keeps on waiting till that is done. Okay. So basically, I would like to mention in summary that this is basically we have a message ordering problem. Okay. And the reason why it is so complicated is because the failures actually make it difficult to figure out what is going on. So what I need to do is the following. I need to somehow get notification of failures. Once I get the notification of failures, I now have to figure out what are all the messages that are sent in the previous view and somehow decide what to do with them. Okay. This we will discuss in detail in the next class. I just want to mention that this is a critical part of the problem, because depending on the messages, you can do various things. You can even delete a whole file system, okay, or something unusual. Okay. So, and for that reason, you may have to think about how to ensure that if you act on a message, it is for the right reasons. Okay. And sometimes the right reasons are meaningful if you look at the order in which it has come. Okay. So our basic idea is that suppose an application can depend on some higher level model. Okay. And what is the higher level model? We talked about group communication systems or the virtual synchrony model. Okay. If that is there, then what will happen is that every party in that system has a consistent view of who are in the group, and therefore any decision, any logic that is written can be consistent. This incorporates whether it is what is a cache consistency, whether it is a question of updating a SAN, various other kinds of things. For all these things, I really need to know exactly who is there, who is not there. If this basic thing is not available, it becomes complicated. Now, hence, there have been various models for group communication systems with different notions and different capabilities. And for example, a Causal model is slightly more difficult than FIFO model, because I have to track dependencies across various events in the system. And a total model is a very easy model for an application to write, but it's too restrictive because every message essentially has to be delivered to all the replicas. Only then you can think of sending the next one. In a sense, it is serializes everything. Okay. and this can be a low performance system. So, ideal thing would be to have somewhere in between these extremes. If you have a causal system, it turns out to be a reasonably good compromise. So, there are systems which employ this kind of models. Okay. I think we will, next class we will look at how these message consistency models are actually engineered. Thank you.